We're going to be talking about quiz results in class, but just in case people needed to look at it again, I thought I would run through this real quickly. Remember that the function for a transformation tells you what to do to each value that you have, each of your coordinates. So this says subtract 4 from the x, add 2 to the y. So if I subtract 4 from the x here, 2 minus 4 is equal to negative 2, and it says add 2 to the y. So if I add 2 to the y, we're going to get negative 3. Remember, the image is the coordinate of the new point. All right, number 2 says double the x coordinate, multiply the y coordinate by 4. So if I double the x coordinate, I get 2. If I multiply the y coordinate by 4, I get negative 16. The next one says move the y position, or move the y value to the first position and change the sign. Okay, so we're going to move the 5 to the first position and change the sign. And then it says take the x and move it to the second position. So the negative 3 is going to go over here, and that's going to be my new point. Okay, I kind of cut back on the directions here a little bit, so basically just ask for the image. I didn't ask you to write a function for this. Remember, reflection over the x-axis, if you've got the point 1, 4, that of course would be 1, 1, 2, 3, 4. That would be right here. The x-axis would be to reflect down here. That would be going over 1 and down 4. So that's going to be 1, negative 4. Remember, the pattern for reflection over the x-axis is that the y-coordinate changes sign. And if you make a graph, it's really easy to see. Sorry, my graph is small, though. A little bit easier for this one. We have 1, 4. It's a reflection over the y-axis, and so that'll reflect right there. That's the point negative 1, 4. Notice when you do a reflection over the y-axis, the x-coordinate changes signs. Translation down 3, 3 to the right, 1 down. Well, 3 to the right would be in the x direction, 1 down would be in the y direction. So we're going to add 3 to the x, and to go down 1, we're going to subtract 1 from the y, and that's going to give us 4, 3 is our new coordinate. All right, the next one, the 90-degree counterclockwise rotation about the origin. If we draw that, hopefully you remember that the numbers will stay the same. We'll still have a 1 and a 4, but the signs might change, the positions might change in the fraction, so or in the coordinates. So remember, counterclockwise is going to be this direction. So I suggest kind of imagining a little rectangle here, and that little rectangle is on a pivot, and you're going to turn that little rectangle on its side. And so instead of being a 1 by 4 rectangle going this way, when you rotate it 90 degrees, you're going to have a little 1 by 4 rectangle going this way. And so you're going back 4, you're going up 1, and that's going to end up being the point negative 4, comma 1. Okay, and hopefully you can see there, if you kind of drew in the angle between those 2 points, you can see that it should look like it makes a right angle as well. But anyway, different people have different ways of visualizing that. But anyway, I don't think it's worth memorizing the patterns, but knowing that you're going to end up with the same coordinates, but just possibly different signs and different positions would really be the key. The last one here, reflection over the line x equals negative 1. Hopefully you know from Algebra 1 that x equals negative 1 is a vertical line passing through negative 1 on the y-axis, which would be right here. We have the point 1, 4. So it's right here. So we're going to reflect it. It's going to go 2 units back to here and then 2 units past that. So if it goes 2 units back past negative 1, that would be negative 2, negative 3, and then it's going to keep a height of 4. So it's going to be negative 3, comma 4 when you put the whole thing together. Down here, the congruence statement. Corresponding parts need to match up. So notice here J matches up with S, so it would be triangle S. W matches up with P, and finally B is going to match up with D, so it would be triangle SPD. They've got to be named in the same order. Okay. For part B, I would encourage you to draw 2 triangles in the same positions and label them the same way. OVE is congruent to GMZ, and then you can see where the corresponding parts match up with each other. If you don't draw the picture, you can actually look at the same positions. OE is the value in the first position and the last position, so that would match up with first and last there. That would be GZ. And you can see in my picture, OE is the base right here, GZ is the base right there, so they match up. Angle E is in the last position. Matches up with angle Z, which is in the last position, and you can see in my pictures E and Z also match up. So that's what's going on there. All right, on to page 2, the triangle congruence rules. Hopefully you didn't miss any of these, or if you did, maybe like one careless mistake, but these should be pretty quick and easy for people. And actually on the test, I'll probably do more of like a proof setup with a given, where you'll label everything in the diagram given using the givens and then decide on the rules. So this is probably a little easier than what you'd see on the test. But again, hopefully you weren't really missing many of these anyway. Remember that the order matters, so you do need to focus on one triangle. Remember that if you had shared parts or that kind of thing, like we have a shared side there or reflexive property, make sure you add those into the diagram. And I suggest just looking at one of the two shapes. They, if they're not both labeled the same way, they're not going to be congruent. So assuming they're both labeled the same way, focus on one of the shapes and just follow along. And you've got to have either the next side or the next angle labeled to be able to continue your chain. So that's a side labeled, and I move around to the next side, and I move around to the next angle. So that would be an SSA, or if you want to spell it backwards, an ASS. Okay, remember there is no ASS congruence. That is not one of our rules. That is none. Okay, for those of you who say, well, wait, there are two sides and an angle, that's side, angle, side. Remember, side, angle, side, you have to have the angle included between the two sides. In other words, the angle has to be formed by the two sides. And notice these two sides are not forming the angle that you're given right there. They're forming this angle over here. Okay, so order matters. That's none of the above. Okay, this one's really easy. We have an angle, the angle next to it, and the angle next to that, that's an angle, angle, angle. We know that triangles can have the same angle measures and different side lengths and not be congruent, so that, of course, is not a triangle congruence rule. Here we've got a pair of vertical angles that are congruent. We have an angle, we have the side next to that, and we have the angle next to that. Angle, side, angle. Remember, for angle, side, angle, the side has to be between the two angles. It has to be included between the two angles. It can't just be any two angles in a side. Now, speaking of which, we have a shared side here. Okay, again, you may want to look at just one triangle, and you've got an angle, and you've got an angle here, and you've got a side. So remember, to make a chain, you've got to have the next side or the next angle. So like if I start here, I've got an angle. I don't have the next side, but I do have the next angle, and then I have the next side. That is an angle, angle, side relationship. Or if you started on this side, side, angle, angle. Okay? You can't go from the angle this direction because you don't have the next side and you don't have the next angle. You can't go from this side over here because you don't have the next angle and you don't have the next side. So it's got to be this direction or that direction. Okay, we haven't discussed that one yet. So for right now, that's a none of the above, and later we'll find out whether or not that's a rule or not. These have shared sides. Hopefully you can see all three sides are labeled for the two triangles. That's a side-side-side relationship. And finally, we've got a pair of vertical angles congruent here. Notice the two sides are forming the angle, which makes that a side angle side case. Again, if you need to look at just one of the triangles by itself, you have a side, you have the angle next to it, and the side next to that. So make sure you are following around the perimeter, because the order in which the sides and angles occur makes this either work or not work. So SSA, not a rule. SAS is a rule. It's not just, do I have two sides and an angle? It's what order are they in? And the easiest way to do that is to follow around the perimeter. All right, for proof here, of course, we have our givens. We know that BC is congruent to CD, and that's given. And we know that AC bisects angle BCD, and that's also given. And so make sure you label everything in your diagram. So BC is congruent to CD. We've got that. Look at your givens, see what it's telling you. We have an angle being bisected, so go identify that angle, BCD. If an angle is bisected, it's divided into two congruent angles. So we know that angle 1 is going to be congruent to angle 2, and that is if an angle is bisected, then it is divided into two congruent angles. Okay. By the way, we now have 2 out of 3 congruent parts. By the way, we should really look at what we're trying to prove. We're trying to prove the two triangles congruent. Notice that there is a shared side there. AC is the same side for both triangles, so we can say that the AC for the triangle on top is congruent to the AC on the bottom triangle, and anything is congruent to itself by the reflexive property, okay? Remember, you got to have 3 congruence statements. That's what I'm going to be looking for. That's a pair of congruent sides. That's a pair of congruent angles. That's a pair of congruent sides, okay? Use your diagram for your triangle congruence rule. Don't assume that just because you put it in a certain order on the page that that's actually the way that it's set up on the diagram. So go to the diagram here. We have a side, we have the angle next to that, and we have the side next to that, okay? It's 2 sides forming an angle. That's the side-angle-side relationship, okay? If I'd ask you to go farther, maybe I'd ask you to prove angle B congruent to angle D or something like that. You could prove the triangles congruent first and then say that the corresponding parts of congruent triangles are congruent. Like B would be congruent to D, or this angle up here would be congruent to that angle up there, that sort of thing. All right, on to our final proof. A lot of givens here. AC is perpendicular to DB. That's a given. And EF is perpendicular to DB. Also a given. And CD is congruent to BF. Also a given. And AC is congruent to EF. Also a given. And anyway, let's look at what we got going on here. So AC is perpendicular to DB. There that is. EF is perpendicular to DB. So we're going to have right angles there and there. So let's go ahead and say that we have those right angles. Make sure you not only label it in your diagram, but you list it in your proof. So we'll say angle 1 and angle 2 are right angles. And the reason being we have perpendicular lines. So if lines are perpendicular, then they intersect at right angles. And remember, it's lines that are perpendicular. You don't have angles that are perpendicular. Lines intersect to form right angles. Okay? Other things here. CD, let's see here. AC is congruent to EF. I'm going to go ahead and mark those two. Those are full sides of my 2 triangles. I'm going to mark that. By the way, we've got these 2 right angles. We know right angles are congruent. Remember, we need 3 congruent statements. Right angles are congruent, right? So if angles are right angles, then they are congruent. Okay, that's a pair of angles there. All right, now we got to be careful. The other thing they gave us in the given was that CD was congruent to BF. Those are not full sides of those 2 triangles. Okay, those are partial sides of the triangles. I would like this whole side of BC to be congruent to that whole side of DF, okay? And we just have this little piece of this one side equal to this little piece of a side there. But notice there's a shared segment in the middle. If I add CF onto DC, and if I add that same CF onto FB, we're going to get this full segment going from D to F and the full segment going from C to B, okay? So I'm going to say that segment DF is congruent to segment CB. That's the addition property, right? I'm adding the same segment to congruent segments. And you could say if a segment's added to congruent segments, then the sums are congruent. But addition property is just fine. And anyway, that's an additional pair of sides. Little hard to label in the picture, but that whole side there is going to be equal to that whole side there. And that should give us a side angle side relationship. We can go ahead and prove triangle ACB congruent to triangle EFD, and that's of course by the side angle side rule. Now let's go back and look at the original proof. Remember, the original proof didn't say to prove the triangle's congruent. I kind of knew where the proof is heading, and I was like, well, those look congruent, so let's prove them congruent. It asked me to prove B congruent to D. But remember, that's the whole point. If the triangles are congruent, then any of their corresponding sides or angles are going to be congruent. So that means that, yeah, angle D right here is going to be congruent to B, but you've got to prove the triangle's congruent first using one of your congruence rules, using your 3 congruence statements that we have here earlier, okay? And then you can say that any sides or angles are congruent. So in this particular case, we can say that D is congruent to B, and that's going to be either the long way. If triangles are congruent, then their corresponding parts are congruent, or if you want to use our abbreviated corresponding parts of congruent triangles are congruent, little shorter phrasing there. So that's what's going on in the final proof.